wrap itself up at the end of 3rd grade and sometimes continues into 4th grade. And there are still some big ideas in multiplication that are really surfacing in 3rd grade that continue in 4th grade. So I'm really glad you're here. Please don't be worried that you don't have a handout. More copies are being made, and we really won't need them until towards the end anyway. So I hope you're next to somebody who you kind of like, and if you don't like them, hopefully you can tolerate them, because we're going to be doing some turning and talking and actually sharing out some strategies. So I invite you to interact in that way with the people at your table. So just to sort of set our agenda for our time together, we're going to be looking at the standards of multiplication for grade 3 and 4. We're going to be talking about how kids make meaning of multiplication, like how do kids view multiplication, and how do we build a conceptual understanding of what multiplication is, since it's more than just learning the basic facts. We're going to be talking then about why it's important to learn the basic facts and how we help kids learn the basic facts at BSI. And then lastly, we're going to be thinking about what are strategies that kids have for developing the basic facts, what are specific lessons that we're doing in the classroom, and then we're going to be talking about some of the games that you can even play at home to help kids learn these facts. So the Common Core standards are now sort of the national standards that the states have adopted. And in their operations and algebraic thinking strand is where you'll find the work of multiplication and division in grades 3 and 4. And so this is long and wordy, but what's really important in terms of standards for grade 3 is this piece here, that children in grade 3 should be able to fluently multiply and divide within 100. Using strategies such as how they relate multiplication and division. And so, for example, if I know 8 times 5 is 40, I could think about 40 divided by 5 is 8. Or using the properties of operations. So that's actually going to be on the next slide. So this is the other piece at the end that's really important too. So this is sort of like very conceptual knowledge about how kids understand the basic facts, but then this last piece is by the end of grade 3, that they should really know by memory all the products of 1-digit and 1-digit numbers. And so that's what we're calling the basic facts. So the previous slide talked a little bit about the properties of operations. And so in this green are kind of like what the 3 properties of operations for grades 3 and grades 4 that are really, really important in terms of multiplication. Okay, so one of them is also a property that they understand in addition, and that's the commutative property. So that's the idea that if I know 4 times 6, I also know 6 times 4. And that's a property that kids tend to understand because it really does move over from their understanding of addition. It works in addition too. 6 plus 4 is equivalent to 4 plus 6. So the next one that they need to understand, and they don't necessarily need to be able to name these strategies as commutative property or associative property, even though we do introduce the language. The associative property is, I kind of like to think of the word associating. Like I can associate with lots of different of my friends. So if I'm thinking about 3 times 5 times 2, I could think about that as 3 times 2 times 5, or 5 times 3 times 2. I could reassociate all of my factors to get the same product. So that's something that they really need to understand. And then the last one is the distributive property. And this is going to be the biggest property that's going to help kids really understand the relationships between the basic facts. And so here's an example. If I'm thinking about 8 times 7, and that's not a known fact to me, I can take pieces of 8 times 7 and put them together. So I could think about 8 times 5, or 5 groups of 8, as 40, and then I could think about 2 more groups of 8 as 16, and put these 2 partial products together, 40 and 16, to get 56. Okay. So then we move to 4th grade, where the standards increase a little bit. So by the end of 3rd grade, they've got some understanding of those operations. they've learned their basic facts, and hopefully they have them by memory, which isn't always the case, which is why we're here. So then in 4th grade, one of the standards that they have to do is they need to be able to multiply a 4-digit number by a 1-digit number, and any 2-digit number and a 2-digit number. And if you notice, it says strategies based on place value and the properties of operations. So those same properties that we just talked about in 3rd grade still apply in 4th grade. And then I just put this up here, even though we're really not going to touch on division today because of the connection between multiplication and division. And also just to sort of get our thinking around the standard algorithm and when it's introduced, is that in division in 4th grade, they need to be able to divide a 4-digit dividend by a 1-digit divisor. So a 4-digit number by a 1-digit number, using the same thing, strategies based on place value and the properties of the operations. They need to understand the relationship between multiplication and division, and they need to be able to illustrate and explain this by using equations, arrays, and area models. So one thing that you'll notice there is that the standard algorithm for division is not a standard. Okay, so our little house with our, I don't even remember what it's called, is not a standard until grade 5. So I kind of want us to go back to the beginning and think about early in kids' thinking and early in 3rd grade. And now in 3rd grade currently, kids have just sort of moved out of a multiplication unit and they're now in a division unit. So they're making sense of both operations sort of around the same time of the year. And they're continually throughout the year working on learning their basic facts. But where do they start? And so I want actually to just, for you to look at this image, and this is an image we've used in the classroom, and I want you to turn to somebody at your table and just describe this picture for them. And yes, I know the soda cans are green. What I'm thinking about more is like, how would you describe the total amount of soda cans? So turn and talk to a partner about that.
Standard 6-pack. Standard 6-pack.
6-pack.
2x3
All right. 4 batches of 6?
Yeah.
Not sure there's more to it.
Yeah. Much else to say about it?
No. I'm trying to think of what the other
4
way.
6-pack? Yeah.
4, 6, 5. Not sure what else. Yeah, case.
I'm just going to raise my hand, and when you see me raise my hand, you could raise your hand, and we can go around the room like that so I don't have to do that, okay? Who is willing to describe this picture to the group?
4 6-packs?
So you're thinking about this as 4 6-packs. So Connie, when you saw this, you saw 1 pack of 6 as a unit. Okay? So it's actually a really big idea in multiplication that's really difficult for kids in the beginning, is that their whole lives they've been counting, and the way that we count is that one object is one thing. And so when we move to multiplication, we start to think about one grouping as one unit, but also 6 items. So this description for 6-packs shows kind of that idea that kids need to be able to unitize. This is actually one of the biggest ideas that have kids struggle with money a lot in the early grades, because you think about a dime, and a dime is one thing, it's one unit with a value of 10. Or you think about a nickel as one unit with a value of 5. So this idea of unitizing comes up, and it's really important in multiplication. Did anybody describe this differently? Would you tell me your names as we go so I can learn them? What's your name?
Anna Piesman.
Good to meet you.
Well, I saw it as a 3rd grader, so I described it as 3 times 2 times 4.
Okay, so 3 times 2 times 4. And where is your 3?
It's the row times the column times the quantity.
So here's your 3, and in terms of soda cans, you're seeing 3 soda cans, and and then doubling it, so that's your times 2, times 4.
I thought that would be easier for the third grader to.
And so, I've actually never had a third grader think of it that way. So then, how would you actually find the total of how many soda cans?
Well, I just figured that not all of them would know what 4 times 6 would be, but it's easier to either multiply, well, they know the doubles since the kindergarten, right? So 3 times 2 they would know, or they would know 2 times 4, whatever is easier
So
for
you're
them.
thinking they may solve this as 3 times 2 times 4, which would make 6 times 4, which is 24. Or you just said something different. You said they may know 2 times 4.
Right.
So they may think about this as 3/8, which is 24. Okay, so if we name what property we're thinking about in order to think about this, we're thinking about this big idea about the associative property. And so images like this bring up these ideas that are big ideas in multiplication. So maybe we describe it differently. 4 groups of 6. 4 groups of 6. Okay, so I wrote your exact words, 4 groups of 6, and if we were going to think about notating that in multiplication, we would be notating it this way, right? 4 groups of 6, making 24 cans. And we can easily see our 4 groups. And so this is actually where kids who have very rote understanding of the commutative property kind of struggle connecting what they know about multiplication and the commutative property to images and situations. So if we're thinking about, according to the commutative property, 4 times 6 is equivalent to 6 times 4. But if I had to think about what does this picture represent, does this represent 4 groups of 6 or 6 groups of 4? Everybody, what does it represent? 4 groups of 6. So when we're thinking about bare number, we can say that 4 groups of 6 is equivalent to 6 groups of 4. And if we wanted to, we could find 6 groups of 4 in this picture. It just wouldn't be as readily easily seen as our 6 groups of 4. So one thing that we're working on with kids is really making meaning of situations. So if I was telling somebody, you know, I'm going to be making all of these bouquets of flowers, and I really want to make 4 bouquets with 6 flowers in each bouquet. That's going to be a very, very different situation than I want to make 6 bouquets with 4 flowers in each bouquet. So where the commutative property is going to help kids is if I could visualize a situation, like I can see that this is 4 groups of 6, but I don't know 4 times 6, but I may know 6 times 4, I can actually use that as my strategy. So the commutative property becomes a strategy for thinking about multiplication, even though it might not match the situation. Okay, so let's look at this other image.
So you're translating the X as groups of?
That's one way to translate it. And so the very beginning place in working with multiplication with students is thinking about equal groups. I mean, there's other ways that we could think about it. We could think about it as multiplicative comparison. So we could be thinking about this as 24
I'm just curious
is
from a
6 times as much as 4.
I'm just curious from a definition standpoint. Like, I would not have distinguished that diagram as either particularly 4 by 6 or 6 by 4. I just said, you know, it's 6 times 4. I would not have been particular about the order.
So in terms of working with kids and thinking about it, we are first defining it as group size. And then we want to broaden their understanding of what multiplication means, because it also can mean as times as many. So I could think about, like I just said, so 24 is 6 times as much as 4, or 24 is 4 times as much as 6. But when we're trying to work from images to build a conceptual understanding of multiplication, we start with the idea of group sub. We also start to think about working in an array. I'm going to flip this because you probably actually can't see the bottom of that chair. When you even see in the dark?
Yeah.
Yes, okay. I didn't mind the dark, but I wasn't sure if you minded the dark. So if we're thinking about an array, and what you probably can't see is actually my grid lines. So I would name this array, it has 5 rows, and it has 4 columns. So I'm gonna, convention has it that we think about rows then columns, and it's really just a convention. So this is a 5 by 4 array. So where this also comes up with kids' understanding of the commutative property, and we've worked with this idea, you've probably seen it on the blog, of the Muffles Truffles context in grade 3, where kids were thinking about putting candies in boxes and thinking about how many candies are all together and how do we know. And so what a lot of kids had a hard time with was, is this the same box? So now I have 4 rows and 5 columns, and convention has it that this is a 4 by 5 box. And so we can say that 5 times 4 is the same as 4 times 5. And in this situation, these are actually the same box. Because if I take this box and I rotate it, it's actually the same thing. So if I hand you the box this way, it's going to be 20 truffles. If I hand you the box this way, it's going to be 20 truffles. No matter how I do it, it's going to be 20 truffles. But let's think about this marble situation. How would we describe this marbles? How many marbles? Sheila?
I would describe it as 4 groups of 3.
So 4 groups of 3. And so is 4 groups of 3 the same as 3 groups of 4? Not in this picture. Yeah. So this is where the idea of thinking about basic facts has to really tie in with kids' conceptual understanding of actually what's happening when you're solving a problem. So we couldn't say this is 3 groups of 4. This is clearly 4 groups of 3. Even though 3 groups of 4 and 4 groups of 3 are equivalent, and they'll both be 12 marbles. Okay? So this is our starting place with kids. We really want them to build the idea of this conceptual understanding of multiplication as groups, equal groups of things. Go ahead.
Do you
Remind me of
ever?
your name. I know we.
I'm Christina.
Christina.
I'm Spencer's mom. Do you ever work with actual objects in which you could take a situation like that where you could dump all the balls out and you could rearrange them into?
We work with, in our array investigation, kids have square tiles and they have tiles to manipulate. So for example, they might have to think about what are all the ways that you could box 20 truffles and then manipulate the tiles that way. And we'll have the tiles available for kids who need it. Some kids can think about that without having to manipulate the tiles. So that gets kids starting to think about things like divisibility. Like if I have 20 truffles, will 2 work? Will 3 work? Will 4 work? How do I know which numbers will work? So not necessarily when we're thinking about equal groups, but when we start thinking about an array model, we do start doing that work where kids are working with different configurations.
I have a question. Obviously, there's a lot of connection between multiplication and division, but are the kids in 3rd grade, like, would they, because we didn't get to talk about it, but I was actually going to describe the 4 groups of 6 as, instead of going, you know, row by column, I was doing 2, 4, 6, 8, like counting by 2s. And for this one,
You're talking about this image.
yeah, but for the other one, you could do 3, 6, 9, 12. So they're like thinking of adding them up to get the answer rather than necessarily.
Oh yeah, sure. And even earlier, than kids understanding about these properties are usually some earlier strategies. And so I guess what you're bringing up is kind of like the difference between big ideas. So like if we're thinking about big ideas, all these properties of operations that we're talking about are really big, big, big mathematical ideas. And then we're thinking about strategies, and you're bringing up that you could have multiple entry points to thinking about how many sodas. And one of the things that you said is, like, I could skip count. Then we were talking about how we could think about it in groups. Okay. So you're starting to think about sort of a developmental trajectory about how kids, and the first thing you actually said is, like, I could think about it additively. I could think about it as, if I didn't have any other entry point, as 2 plus 2 plus 2 plus 2, or I could think about it as 6 plus 6 plus 6 plus 6. And that's a lot of the work that we try and do too, is to connect addition to multiplication. Like, here's our 4 sixes, or our 4 groups of 6. So that's an entry point into multiplication, is kids making sense of an operation they already know, which is addition. And so this is kind of early on the landscape of thinking about multiplication, and then we want to move kids away to be able to think in groups.
Marcy, I just want to add here that you'll notice that in terms of kids building schema, that repeated addition that Marissa brought up, you'll notice that there's not, what comes after the equal sign is not necessarily the answer, right? We're trying to get away from that answer, and we're trying to build schema for equivalence, the idea of equivalence, the idea that 4 groups of 6 is equal to 6 plus 6 plus 6 plus 6. And Jason, going back to what you said, what you asked about that of, groups of, when you, later on in 5th and 6th grade, when the kids really get to thinking about fractions, that of word really comes into play with their understanding about how to deal with fractions, which is very difficult. So again, all of this groundwork is being laid in the earlier grades to build that algebraic understanding that comes into play later on.
Yeah, that piece of equivalence is really, really huge in thinking about that. And like we said back here, thinking about these properties, about these 2 pieces being equivalent. All right, so let's, oh, go ahead.
Comment to the next picture, you said we couldn't really say these are 3 groups of 4, but I think we could. If you focus on the colors, it immediately is obvious. For me, it's like 4 blue, 4 red, and 4 green.
Oh, that's interesting.
And I would hope that we would encourage our kids also to give that answer, to be out of the box thinking.
We, of course, encourage didactic thinking. Like, we don't want, I mean, part of what underlies our entire philosophy about mathematics is that there is not one way to solve any one problem. And of course, to think about the question, how many marbles, if that's our question, to think about, well, I saw the colors as 3 groups of 4 is a completely, you know, it's a solution. Yeah, thank you, viable answer. That completely makes sense. I think the point I'm trying to make, though, is our purposeful choice of images to help kids construct understanding, to bring up all the properties, and to kind of play around with some of their confusions. Like, we know when we're talking about this investigation, about this chair's moving crazy, about Muffles Truffles, we know that we're going to have very rich classroom discussions about, is this the same box, or did we repeat a box here? Like, is a 5x4 box the same as a 4x5 box? Because that we're understanding how kids' development happens, we're expecting to have these conversations with students to sort of make sense of these operations. So I'm not going to read this because we've kind of talked about all that stuff. So basically, all of this early work in multiplication is really what paves the way to even have them move in the direction of memorizing their basic facts. We would never want to start working on basic fact work before we built all this conceptual understanding. And so I wanted to share with you, I have a good friend who was a coach at PS 503 and now works for Metamorphosis Learning Communities, which is who we work with as our staff developers for math as teachers. And she has this interesting dialogue with this little boy, I think his name is Kevin, around this problem, 8 times 9. And I want you to really just, I'm going to sort of role play the dialogue, and I want you to think about this student and how this student has learned his facts. I want you to also think about how will this help or hinder his understanding of multiplication based on all the ideas that we talked about. So Kevin turns over a flashcard and he says 8 times 9. 8 times 9, and he puts up his fingers and he starts to count. Okay, 9 and 9 is 18, 19, 20, 21, 22, 23, 24, gets to 30. And Sonal says to him, that looks like a lot of work, what you're doing with your fingers. What problem is it that you're working on? And Kevin says 8 times 9. Oh, 8 times 9, that is a hard one to remember. And Kevin says, yeah, I keep forgetting it. So Sonal says, is there anything that you know that can help you remember? And Kevin says, well, I know the answer is on the back of the card. I could look there, that would help. And Sonal probably chuckles and says, I was thinking more about another fact that you know that might help you. So Kevin is really puzzled. He asks Sonal, what do you mean? And Sonal asks him, do you know 8 times 10? He says, sure, that's a really easy one. It's 80. I knew all of my 10 facts in 2nd grade. So Sonal says, well, that's terrific. Here's what I'm wondering. I'm wondering, how might you use what you know to help you figure out what you don't know? You know that 8 times 10 is 80. How could that help you figure out the product of 8 times 9? And Kevin laughs and he says, it couldn't. They're different facts. And he goes back to counting on his fingers. So I just want you to turn to a person next to you. What do you think about this vignette? What does this bring up to you about Kevin's understanding of the facts?
I think he was right about the card.
That's a smart idea.
My concept of importance to understand that 8 times 10.
I guess what she explained before, they don't know that 8 times 9 days.
It's too locked into the one approach.
I think being good at math means being good at cheating. But I mean, also like cheat because you know 80,
Right.
and then find some strategy. I never talked about strategies in school. Like, they didn't have that.
No, it was all rote memorization.
But like, I thought I was too lazy to memorize the 9 books, right?
Yeah.
And I thought
I know.
I would do what they're talking about, and I thought it was cheating.
Right.
But I was like,
Right.
I'm not gonna tell anybody.
As I actually hear you talking to each other, I actually hear some people sharing their own experiences of how they learn their facts, which is probably very likely like my own experience of learning the facts, which was all about memorizing them. And I have not a very good memory, and as I look back to my childhood, I was the same person then as I am now. And I really struggled learning my facts because I had no understanding of the relationship between them. So I want to point out this vignette between Sonal and Kevin because of what the standards say. And so one thing that the standards say is this word fluently, that kids need to be able to fluently multiply within 100. And so I brought up this vignette to have us kind of think about what does it mean to be fluent with your facts. So fluency is when kids have a network of number relationships and they can use that understanding when they don't remember them. That's what fluency is. Automaticity is when students have automatic recall of a fact, but they don't necessarily understand the connections between the facts. Okay, so do you hear how they're different? Okay, so we want automaticity, but we also want fluency. So I'm not saying that automaticity is not important, and it's actually in the standards that we want kids to be automatic with these facts by the end of 3rd grade. But we don't want automaticity without fluency, which is something where we want kids to have those relationships. So is Kevin fluent? What's your gut response to that? No, he's not. He has automatic recall of 8 times 10. He doesn't even have to think about that. But he's not fluent because he has no way to derive a fact from another fact when he can't recall it. He sees no connection between 8 times 10 and 8 times 9 and how one can help him with another. So research has actually shown when we're thinking about basic facts as isolated bits of information, and that they learn them through rote drill, like flashcard work, even computer work sometimes, that they actually have more difficulty remembering them. And you'll hear this, because you'll hear kids say, so I'll say, what's 7 times 6? Is that the one that's 42, or is that the one that's 56? So they know that both of those products are the answer to some kind of fact, but they're trying to put the pieces together. But that's not fluent understanding. That's, I'm trying to remember what I know I'm supposed to remember. Okay? So on the other hand, when students are given an opportunity to build these relationships among the facts, they're better able to retain them. So what are these relationships between the facts? That's what I want to talk to you a bit about, and then we're going to look at some games. So talking about isolated bits of information, look at all the isolated bits that kids would have to remember. It's quite a bit. There's kind of a trajectory to how kids normally learn their facts, and you'll be seeing that there are some in red and some in highlights. So many times kids understand the property of 1. They understand that 1 times any number is itself. Okay? So with the commutative property, if I understand 1 times something, I can switch that and know that something times 1 is also going to be itself. So kids can solve 1,000 times 1 pretty easily. So where we go from there when kids develop is that somebody had brought it up earlier, that 3rd graders and kids younger than that kind of understand this idea of doubling. And so the idea of doubling is inherent in this times 2, those facts. And then with the commutative property, thinking about 2 times something or 3 times 2. So here's where we really want to start building from what kids know. And so if kids know 2 times 5, could they double the product for 2 times 5 and think about 4 times 5? If kids know 2 times 9, this is a fact that kids tend to struggle with, 4 times 9. Can they use 2 times 9 and another 2 times 9 to think about the product of 4 times 9? So these are the relationships that we're talking about. Okay? So similarly, we could think about if we know our 4 times facts, that could help us with our 8 times facts. So this big idea about doubles and doubling is actually huge in understanding the relationships in our multiplication facts. So we even saw Kevin know 10 times, and he didn't seem like he wasn't fluent. So a lot of kids, even as young as 2nd grade, have this understanding of something times 10. And so kids understand their facts of 10, but could they think about their facts of 10 to help them think about timesing something by 9? And when we really think about the facts that kids struggle with, what they end up struggling with is their times 7s, their times 8s, their times 9s, and sometimes their times 6 facts. So we're actually seeing that 6s and 8s, we could be thinking about using doubling strategies. But what do we do when we think about times 9? And what we're really trying to get kids to do is use what I know about 10 to help me with 9. So and this is where our groups of language is really, really important. Because I want to think of, if I have 10 groups of 7, but I only need 9 groups of 7, how many groups of 7 do I need to remove? 1 group of 7. And so we want kids to be able to use the distributive property. So I want to be able to take 10 times 7 and subtract 1 group of 7. I'm sorry, subtraction. 10 times 7, remove 1 group of 7 to help me think about 70 minus 7, which is 63. This group sub language is really important because when I adjust, so I know I'm gonna start with 10 groups of 7, but now do I remove the group of 9 or do I remove the group of 7? So if I'm not thinking groups of, do you hear how the language supports you in thinking about what to adjust? If I just said, okay, 9 times 7, okay, I could do 10 times 7, but then they might remove a group of 9. So really thinking about sticking in that groups of language really supports students and even using the distributive property. And you could use a distributive property. This is called the distributive property over subtraction because we're removing a group, but you could use a distributive property over addition when you're adding on a group. So I'm not going to go through the rest of all these relationships, but I want you to just think about this with a partner. If your memory failed, and oh, see, I gave away my example. If your memory failed, it was in my head, and you couldn't remember the product of 9 times 7, how many different ways could you derive its product? So I want you to turn and talk to somebody next to that.
I guess the obvious one.
Other than the answer we already have.
7 9 times.
3 times 7 times 3.
5 times 9.
I do 5 times 9 and add 2.
Yeah, I think I don't actually remember the 9s. I just
I could take it down.
I do the subtraction. But I always remember the digits have to add up to 9.
Yeah, or 3.
Yeah, exactly.
Cheating.
That's a good cheat.
But it's a good
Anything's
cheat.
allowed.
I've been told that to my is that it only works for 3s. It doesn't work.
Yeah, that's a good one.
I mean, if you know like your squares, like 7 times 7 or 8 times 8, you know, I guess you could say 49 plus 14.
Right. Those are good like anchors.
Yeah, so that's 3. Right.
So hopefully by now you've gotten to talk about at least one
I'm-
alternate strategy. So we already have it up there that we could use 10 times 7 to help us with 9 times 7. So did anybody
just
think
another
of
five.
anything
Yeah,
other
this
than
is
that?
true. The 9 times 4 is like just
9 times 5 plus
Is
2.
that just-
Okay, so you're thinking about 9 times 5. That's a fact that a lot of kids know.
Plus 9 times 2.
And you're thinking about 9 times 2. What's 9 times 5? 5. And 9 times 2 being 18. And then putting together those products. Okay, so here you have the distributive property over addition, where we're thinking about 9 times 5 plus 9 times 2 being equivalent to 9 times 7. So we're actually modeling this notation for kids. And we're not expecting that right away that they're taking it on, but some kids will. And we want them to start internalizing how to notate their work. Because a lot of times what kids will do is we're talking about this meaning of the equal sign, and a lot of times kids will do this. It's kind of like a run-on math sentence. It's like all of the steps in my mathematical thinking, but not thinking about the equal sign as equivalence. So really being very clear, like this is my first step, and this is my second step, and this is my third step, and this is how I can think about showing that property.
This may be sort of a stupid question, but if they were to go about it that way, when they're adding 45 and 18, do they know how to add double-digit numbers like that?
They should by the end of second grade.
Okay. And they stack them? Is that how they do it?
That's a whole other workshop.
Because I wonder when we get, I'm just curious in terms of helping, when you get to that point.
In third grade right now, we're developing understanding. I'm sorry, in second grade right now, we're developing understanding of the traditional algorithm for addition and subtraction. But the traditional algorithm for addition and subtraction is not actually a standard until grade 4. Even until grade 3, it's strategies based on place value.
Right, that's
So
why
they
I'm
could
asking.
use the algorithm, but they'll likely do 40 and 10 and then 5 and 3 and then
Okay,
add those
okay.
parts together. Did I do that right? So it's 50,
Yeah.
63. Okay, what's another? So starting with the fact I know and adding on. Let's just take one more. Did anybody think about it in a different way?
Well, we had two strategies. So one was similar to the strategy which we had for year 10s when we did 3 times 2 times 4. So what we did is we broke out 9 into 3 times 3 and then multiply that by 7 because we figured that the third graders would rather know the 3s
Okay, so you're starting with
than 9.
I know 9 is 3 times 3 times 7. And then, so you were factoring out the 9.
Right.
And now you're thinking about, so how will this make my work easier?
Well, they probably will know 3 times 7.
So now you want to associate my 3 times 7. So you've changed this into 3 times 21.
Right. And that would be
And that would be
easier.
63.
And then another strategy which we had is we again broke 9 because I thought 9 is a more challenging number than 7 for them. Into 4 plus 5 and then times 7. And then they would multiply 4 by 7 and then 5 by 7.
So you thought about this as 4 times 7 being 28, and 5 times 7 being 35, and then those partial products of 28 and 35 being 63. So in the end, you were thinking about 9 times 7 as 4 times 7 plus 5 times 7. So if those were 2 facts that a kid knew, which they could put them together to
So
so 9
it's
times 7.
3 times 7 or 4 times 7 or 5 times 7 are easier facts for them than 9 times 7.
So all these strategies is what we're talking about when we're talking about kids being fluent. And I had another piece that I actually think I have a whole other segment to do a whole other workshop for you at another day. But I want to move into the games portion because I want to send you home with something. If somebody could get the lights, that would be helpful because I think now we probably actually need to see. So I'm not going to go through the first game with you because Rolling Thunder is actually a really pretty easy game. And if you have a 4th grade student, I wouldn't work on Rolling Thunder with your 4th grader unless they're really, really strong. It's a very early multiplication game that really gets back at that idea of groups of and has kids work with that language. So all you need is 2 dice, but the dice you need is you need actually 1 numeral die and the dot die. That's really important to differentiate the 2 factors. And so all you're doing is you're rolling the first die and it's telling you how many groups, and you're rolling the second die and it's telling you how many are in a group. So I'm going to think about this when I roll as 3 groups of 4. And then you'll see your game board on the second page as you just cover the numbers. And you just cover the numbers until your board is full. And then if you'd like the kids to practice some notation and thinking about that language, there's a recording sheet for Rolling Thunder that you can copy. Okay. There's not a lot of strategy in that game, but there's a lot of practice in that game. Where the game falls short, though, is that you're only going to be practicing up to products of 36, because a die goes up to 6 by 6. Okay? So if you turn the page, I'm going to have you play multiplication tic-tac-toe with a partner. So this is how you play. You have your game board, and you need 2 paper clips. And then you have your counters on your table, hopefully, that you're going to use to cover the places on the board. And it's called tic-tac-toe, but it's kind of more like bingo, because the idea is that you're getting 4 in a row. So you're trying to cover 4 in a row. So you should pick one color and your partner should pick another. So in all the boxes are all the products. And on the bottom is all the factors. So for example, if I pick, I'm going to take my paper clip, and let's say I put my paper clip over 3 and over 5, and I say 3 times times 5 is 15. I'm gonna take 15 and I'm gonna cover 15. My partner, it's their turn now, they can only move one paper clip. So they have to decide, are they gonna move it away from my factor of 5, or are they going to move it away from my factor of 3? So let's say they shift it, now they do 3 times 8. 3 times 8 is 24, and they're gonna cover 24. So the goal of the game is to cover 4 in a row. Okay, so just take 5 minutes to play.